Hey everyone, welcome back. In this video, we are going to discuss about the uniqueness of identity relation defined on a set. So let's get started. At the very outset of the video, let me pose you a very simple question. Don't worry, we'll be able to know the answer to this question at the end of this video. So here is my question. Is it possible to have more than one identity relation defined on a set? That is the identity relation unique or not? My answer is yes, identity relation is unique. Obviously, you have the right to ask how. Let me prove my claim. First of all, my claim is that identity relation on any non-empty set is unique. That is, you cannot have more than one identity relation defined on a given non-empty set A. Let me prove my claim. So before proving my claim, note down that in my proof, I am going to use one of the proof techniques, which is known by the name of proof by contradiction. So let's get started. Note down that I am going to prove my claim for any set. So in my proof, my set A will have no speciality. It is an abstract set. Its elements could be anything. It means that once we prove our claim, we can without any doubt say that on any non-empty set A, identity relation is unique. So let us suppose that I have the set A which is not equal to 5. I mean my set is non-empty. Let my set A is non-empty and let it be arbitrary. Okay? And let us also suppose that I have two identity relations, delta A and delta A dash. Let us suppose that delta A and delta A dash be two identity relations on the set A. My job is to prove that delta A is equal to delta A dash, because that will prove the uniqueness of the identity relation. Because I am going to use proof by contradiction method. So let us suppose that delta A is not equal to delta A dash. So since delta A is identity relation by hypothesis, what does it mean? Let us apply the definition. It means that for all A comma B belonging to the set A comma A is in the relation delta A. Also, the ordered pair A comma B does not belong to the relation delta A, I mean the identity relation delta A, with the property that A is not equal to B. Don't worry, there's nothing but the implication, in fact the definition of identity relation itself. Now, once again, since delta A dash by hypothesis is also an identity relation, it means that for any two elements A and B of the set A comma A must belong to the identity relation delta A dash, as well as any ordered pair of the form A comma B with the property that A is not equal to B. The ordered pair A comma B must not belong to the relation delta A dash by the definition of identity relation itself. Now, by this first supposition, delta A is not equal to delta A dash. And as you know, delta A and delta A dash are relations, and basically relations are themselves sets. What does it mean? What does it imply? It implies that there must be then at least one ordered pair in one of the relations delta A or delta A dash, which is not belonging to the other. Only then delta A is not equal to the delta A dash by the definition of equality of two sets, because relations are themselves sets. What does it imply? Delta A dash delta A is not equal to delta A dash. It simply implies that there exists then an element, at least one element x naught in the set A with the property that x comma x belongs to one of the relations, say delta A, such that x, the ordered pair x naught comma x naught, does not belong to the relation delta A dash. Why? Simply because delta A is not equal to delta A dash by our supposition, by our assumption. So obviously, by applying the definition of equality of two sets, there must be then at least one ordered pair, which I have denoted by x naught comma x naught, which belongs to one of the relations and does not belong to the other one. So this implies that there must be then at least one element in the set A such that the ordered pair x naught comma x naught belongs to the relation delta A, and the ordered pair x naught comma x naught does not belong to the relation delta A dash. Or you can say, in other words, there exists an element x naught in the set A such that x naught, the ordered pair x naught comma x naught, does not belong to the relation delta A dash. What does this imply? It simply implies then that delta A dash is not identity relation. So we have delta A dash is not an identity relation. What? Is this possible? This clearly goes against our hypothesis. That is, delta A and delta A dash are identity relations. But here I am contradicting with my hypothesis. That is, delta A dash is not identity relation. But according to my hypothesis, my delta A dash is in fact an identity relation. But here, delta A dash is not an identity relation. How is this possible? This is not possible. I am contradicting myself. So, what is wrong with this? Is there anything wrong? Yes, something is wrong there, definitely. So, where is the fault? The fault lies simply in our assumption that delta A is not equal to delta A dash. It implies that our supposition that delta A is not equal to delta A dash is simply wrong, because we are getting contradiction to our hypothesis. If delta A is not equal to delta A dash, what does it mean? It means that its negation is then true. Of course, its negation is then true. This implies that its negation, what is the negation of delta A is not equal to delta A dash? Simple, its negation is delta A is equal to delta A dash. If this is not true, obviously its negation is going to be true, and its negation is delta A is equal to delta A dash. This proves my claim, and my claim was identity relation is unique. Thus, we can now say that an identity relation on any non-empty set is always unique. Note down that in mathematics, once we complete some proof, we use this notation or this notation. This QED is simply called error demonstrata. From now on, we will use the not an before the phrase identity relation. Why? Because we have just proved that identity relation is unique.